Hello and welcome to the Inlet Protection Comparison for Sediment Control on Roadway Construction's webinar. My name is Paula Hyman from the Ohio LTAP Center, and I'll be your technical support for today's webinar. Just a couple of housekeeping items. If you have questions throughout the presentation, please put those into the questions box and our presenter will address your questions at the end of the presentation. The webinar is being recorded, and providing that the webinar recording is successful, I'll send out a YouTube link with this at the end of today's presentation. So I want to thank you in advance for your participation, and I'll pass things off to Anil, Director for Water Resources with MS Consultants. Anil?
Good afternoon. Thank you, Paula. Good afternoon, everyone. Thank you for joining today for our research presentation. Again, the title is Inlet Protection Comparison for Sediment Control on Roadway Construction. This is an interesting research project that MS team has been working on since 2019. Here today, we're gonna talk about the details of this project. Before we do that, I'd like to introduce myself. Again, Anil Tangerala. I'm with MS Consultants Inc. And with me today are two presenters. I have Justin Kearns, who is also with MS Consultants, and Ryan Winston, who is he's professor at the Ohio State University. So the three of us today are going to be presenting on this topic today. Just to give you, with the research team, MS was the principal investigator for the project. We also did an extensive product research and worked on the design recommendations. Ohio State was the co-principal investigator. They did the full-scale product testing and also the data analysis. And we had great, I guess, ODOT's Planning and Research Technical Advisory Committee with Becky, Hans, and John have been instrumental and have been providing valuable input throughout the research project as well. So definitely want to thank them. And so that's the research team that worked on the project. Next slide, please. In terms of the outline for the presentation, I think we're going to talk about the background for the project. Why exactly did we look at inlet protection devices? As you all know, inlet protection devices have been fairly common and used for sediment control for various projects. The applicability of roadway projects was what ODOT was concerned about, and we were looking at how to see the efficacy of those products for roadways. So I think we're going to talk a little bit about why we looked at that and the objectives of this project and the timeline. We did an extensive research with the inlet protection devices and practices. We looked at various types of practices and how that applies to the roadway. We're going to talk about that. With OSU, we also did an experimental design of actually creating a mock roadway and looking at these products practically with various flow scenarios, as well as performance and longevity testing. And we also analyzed the results and came up with design and maintenance recommendations. So our goal today is to kind of talk through these and ultimately, answer any questions you may have. So now I'm going to turn it on to Justin Kearns, who's actually going to be talking about the research background.
All right, thank you, Anil. So a little bit of background on the project. Obviously, any type of construction project is going to require grading and exposing bare subsoil to natural forces. This results in sediment and erosion, which can convey pollutants and heavy materials, bacteria, nutrients, and other things downstream to our receiving waters. The downstream effects of this are obviously impacts to the environment, things such as reduced ability for fish to find food. It's going to clog gills, has very disruptive impacts on aquatic habitat, and it can reduce capacity for channels, streams, and reservoirs to convey flow, and a lot of negative biological consequences. It can also impact our other constructed stormwater management techniques, such as permeable pavers, bioretention, by clogging them with sediment. So for ODOT in particular, one of the main sediment and erosion control practices they implement is inlet protection. These are very prevalent on the linear roadway construction environment. And the Ohio EPA has several approved inlet protection practices they currently implement. However, a lot of these practices are not very applicable and not super conducive for the roadway environment. For example, a lot of them involve loose gravel and aggregate in order to function, which is not an ideal characteristic to have along a travel lane near moving vehicles. It can pose a safety hazard. These practices also function primarily through ponding water and have sometimes very substantial detention times and will pond water for longer than ideal. Obviously, spreading water onto a travel lane can lead to hydroplaning and other safety factors for vehicles and pedestrians. So that was kind of the impetus for this project. Is ODOT wanted to look at one of the many manufactured devices that are currently on the market. Many of these devices are designed specifically to counteract some of these roadway-specific design needs. But there's so much material and so many products out there that ODOT wanted to do a little research on their own to inform their decisions and find out which products were suitable for the roadway environment and which ones operated efficiently. So some of our goals and some of our objectives for this project is we wanted to first develop a comprehensive list of all the proprietary products that are available, as well as any of the generic or AKA non-proprietary products. And then we want to understand how these inlet protection devices, which we refer to as IPDs for short, how they perform and what the critical variables that we should be looking at in order to evaluate their effectiveness. So those include sediment removal, ponding depth, the longevity, and then the ease and frequency of maintenance required to keep them operating functionally and effectively. And we wanted to provide this data to ODOT so that they could incorporate it into their decision-making process when they evaluate inlet protection devices and ultimately inform a future qualified products list that they can reliably count on for use for their projects around the state. The research timeline, as Anil alluded to, we began this research in September of 2019. It started with a comprehensive literature review of past research efforts on this topic. We wanted to see what other states, what other DOTs, other universities, what other entities had done in this field and what kind of studies they had done and how we can improve upon those studies and make this as successful as possible. We also did some sampling of active ODOT construction sites, and that allowed us to better characterize and better understand the sediment loads that we experience in Ohio. And we were able to tailor our testing parameters to match what can be expected in the real world scenario. Then we developed a comprehensive list of all the products that were available, and we developed criteria for how we were going to evaluate those products, and we designed a sediment and erosion control testing facility on Ohio State's campus, which Ryan will talk about in detail later on. And so starting in September 2020, we actually began construction of this full-scale testing facility, and we performed performance testing on the products. We performed this testing on both the proprietary and the EPA non-proprietary products. Following the performance testing, we then followed that up with longevity testing, which again Ryan will explain in detail later on. And then here in March 2023, we're wrapping up the project and we're providing our recommendations to ODOT, which will be made available upon final publication of the report. Moving along here, there were four main types of inlets that we looked at for this research project. These are the four most common and most prevalent inlet types in the ODOT roadway environment. There's the grate only, which is a catch basin number 5. These are typically within drainage ditches and swales along the roadway. You also have the median inlet, which is a curb opening inlet on a curbed roadway, but no grate. And then that is inlet number 2. The catch basin number 6 represents the grate only configuration along a curbed roadway. And then a catch basin number 3A is the combination grate and window opening located along a curbed roadway. So we focused on practices and products that were designed to fit these 4 specific inlet configurations, as they'd be the most applicable and would give ODOT the best understanding of what devices would work best for their projects. So we started off looking at, again, the Ohio EPA practices. These are the non-proprietary, the generic practices. These are not trademarked. There's no specifically manufacturer for these. They're comprised of typical construction elements, such as geotextile fabric, wire mesh, aggregate, excavation, etc. These are typically built by the contractor out in the field, using the materials they have. And these are the ones that, again, we wanted to test to see how they perform, but then we also compared the proprietary products to these already approved EPA products to see if these proprietary products could perform to the same sediment removal level, provide the same water quality benefits as the EPA products, but in a more compact form and functional package that would better work for ODOT. And we found that these proprietary products came in 5 basic configurations. There's the above grate enclosure shown there on the top left, and these essentially attach to the grate or the inlet, and they're 4-sided or round, and they are kind of 3-dimensional domes that sit over the grate. These are most applicable for the grate only within a ditch, not within a roadway, because they have a surface kind of obstruction because they pop up like that. There's the undergrate basket. These are applicable to grate baskets, both in the roadway and not in the roadway, and they typically attach to the frame or to the grate, and they hang below the inlet to catch sediment. Wattles are very common practices. These can come with a variety of materials, both a variety of fill material, as well as a variety of netting or outside kind of tubular material to hold it in place. And they can be used on roadways or in ditches and non-roadway elements. The curb inserts are similar to wattles, but they're actually designed to sit within the inlet, the curb inlet opening. So they're kind of recessed out of the, recessed into the inlet opening itself. And they're applicable for curb openings only, not for grates. And then there's the grate cover with a curb attachment. And so these will cover the grate, but then they have an optional attachment that will also protect the window opening along the curb as well. So now I'll turn things over to Ryan, and he will talk about the experimental design and the testing of the products. Ryan, it should be all yours.
Fantastic. Thank you very much, Justin. I'm going to take you now through the experimental design and then also a bit on the data analysis and what we've learned from the controlled field testing that we conducted. So we'll start out with a 30,000-foot view of the experimental design, and then we'll drill into some more of the details here. So the gist of what we did was we created a controlled testing facility at our Worcester campus, which included, and as you can see in the top left, a water supply. We pumped from a pond to a series of 5,000-gallon storage tanks, and then we could use that stored water to essentially create flow to each of these inlets. We did so using another pump into a mixing chamber that you can see in the top right-hand part of the slide. That mixing chamber is where we added the sediment to approximate typical construction site runoff that's not yet treated. And then that water flowed off of the back of the trailer that this whole system was housed in and onto either the road or the ditch section that we were testing. From there, the water flowed through what was an unvegetated section of either road or ditch to approximate conditions, worst case conditions on a construction site, into an inlet, and that inlet contained the IPD that we were testing. From there, the water flowed through a pipe system to sediment basins, which were required in order for us to get the permit to construct this testing facility. A plan view of what we saw on the last slide is really shown here. On the left-hand side, we have our storage tanks. We had 30,000 gallons of capacity that were all plumbed together. We drew from that for each of our tests. You can see we built 3 different curved road sections, 1, 2, and 3 in order here, and then also a triangular ditch section to the north. with the 4 different types of inlets that Justin mentioned. You can see our trailer here that was where we were pumping water from the tanks through and adding our sediment. That sediment then discharged down onto the road section or the ditch, depending on what type of IPD we were testing. And then we could measure water quality upstream, immediately upstream, and immediately downstream of the IPD to understand basically the net difference between those two is what has been trapped or removed from the stormwater. On the right-hand side or the eastern side of this picture, you can see the sediment basins, which provided secondary treatment and are not going to be discussed further in this presentation. So how did we create our simulated runoff? We essentially used the same exact type of hydrograph for each of the runoff tests that we conducted. That runoff test was informed in terms of its hydraulics by the rational method, which you can see here. So Q equals C times I times A. The C was taken to be for bare packed soil that would be relevant on a construction site. Our time of concentration on these inlets is going to be very small, and so we went with a very small time of concentration. As we looked at the rainfall data, we pulled about 70 years of historical rainfall data for Columbus and essentially used a rainfall intensity of around 1/2 inch per hour in this calculation, and that would cover about 98% of the rainfall intensities, the hourly rainfall intensities over that time period. So we felt like we were conducting these tests at a rate of flow that approximated a relatively large size storm that was very infrequently exceeded. And the areas were taken from typical curbed inlet or median inlet drainage areas that we found on various roads that we had analyzed across the state of Ohio. From this combination of factors, we used constant flow rates of 0.16 and 0.29 cubic feet per second, as you can see there, for the curbed roads and the median inlets, respectively. So that was our test flow rate that we conducted at a constant rate of flow for a 30-minute period for each of the tests that we conducted. The other thing that we really needed to get our hands around was to understand what sorts of characteristics of sediment we needed to add to the water in the form of total suspended solids. And so what we did is we did a study on 3 different construction sites in central Ohio, where we collected 49 runoff samples from active construction sites that ODOT was working on to benchmark sediment concentrations for use in this project. From that, we were able to ascertain that typical construction site runoff had roughly a 1,000 milligram per liter concentration as a middle value. There was a lot of spread around that 1,000 milligram per liter number, but that as a middle value, that was the number that we were sort of aiming for. And doing some calculations came up with needing to add 35 and 55 pounds respectively of sediment for the curbed road and ditch road tests to get to a proper influent concentration for the testing. The other thing that we did with our active construction site samples is we measured particle size distribution to understand the percentage of sand, silt, and clay in that runoff. You can see that here in this simple table. This was characterized as either a silt loam or a silty clay loam, which we felt very good about because the subsoils here in Ohio tend to fall into those 2 textural classifications. So, this particle size distribution is what we aimed to match as part of our testing. I think we did a pretty good job of that. We measured about 1,000 particle size distributions as part of this testing, and we're able to fairly well match that relatively silty and clayey mixture. Okay. In terms of runoff preparation, you can see some pictures here. We're pumping from our tanks in the first picture into the mixing tank in the second picture. We have a baffle in that mixing tank in the third picture that is there simply to to basically take some of the velocity out of the water as it's coming blasting out of the pump. We've got clearly orifices there that allow the water through the baffle. And then we're adding our sediment, as you can see in the fourth picture, downstream of that baffle as the water is exiting the back of that mixing tank and flowing down the back of the trailer, essentially the tailgate of the trailer, if you will. And this particular picture is a curved road section. You can see the curved road here on the left-hand side of the picture. And again, we're approximating a worst case scenario where we don't yet have asphalt or other erosion control down on our road construction site. We had two different testing protocols that Justin mentioned earlier. The first that we did was performance testing. This was to test new unused IPDs. We installed all IPDs per manufacturer specifications, essentially poured over their literature for their particular IPDs, and did 3 tests for each IPD. So we ran this in triplicate, and for each of those tests, we used a brand new IPD. And in between tests, we completely reset our testing facility. So we cleaned the gutters and the catch basin with shop vacs, with wet dry vacs, to remove any accumulated sediment and really set the baseline of this particular site back to a ground zero, if you will. As I mentioned, each of the tests was performed with a 30-minute duration at a constant flow rate, and I mentioned those flow rates earlier. The second type of testing that we did actually last year in 2022 was longevity testing. This was performed after the end of the performance testing. We picked essentially half of the IPDs that we tested in performance testing for testing where we were applying repeated storm events to the same IPD. So we applied 5 successive simulated runoff events without any maintenance or replacement of IPDs, and we were really looking here to try to inform maintenance intervals, understand failure modes if they occurred, and then really to try to understand how these systems would perform on a real construction site, right, when the IPDs are no longer brand new. For these tests, we did have a 24-hour duration between each test, again, to allow the sort of the test site to reset itself. We did not clean out the gutter and catch basin between the longevity tests. We allowed each of the successive storms to move sediment as it might, and tested the IPDs, the performance of them in each of those 5 tests. We took pictures, videos, notes, really copious amounts of measurements to inform data analysis and inform the presentation, the final presentation that you're hearing today. Our monitoring design was relatively simple. We had a pressure transducer that was located immediately upstream of the inlet, so we could measure the level of ponding upstream of the IPD. Obviously, tremendous depths of ponding are a negative on a road construction site where we might get water ponded out into a travel lane, which clearly is undesirable. So we were measuring that on a 1-minute interval. And then we were also taking samples every 2 minutes throughout this 30-minute test, immediately upstream of the IPD and then immediately downstream of the IPD in the outlet pipe that drained the particular type of inlet that we were working on that day. We took these samples with automated samplers, and we composited all 15 of the samples that were taken during each hydrograph into a single sample so that we could get an idea of the event mean concentration of sediment upstream and downstream of the IPD. From there, we took our samples back to the lab and essentially did 3 different types of tests on them. The first was TSS by vacuum filtration. The second was turbidity analysis using a Hawk 2100Q. And the third was particle size distribution using a Beckman-Coulter laser diffraction instrument. Those are all sort of standard methods for sediment analysis in water. And so I'm not going to spend more time on it than that, but those are the 3 things that we characterized as part of this study. I'm really going to focus in on the TSS and turbidity measurements in this particular presentation. Okay, before we dive into the data analysis on the next slide, I want to spend just one more slide thinking about definitions here of critical ideas or critical pieces of information. So the first is bypass, and bypass is really unintentional flow moving around or under an IPD, and you can see an example of that here where the water is going behind the curb guard. It's basically untreated discharge of water into the sewer system that is unintentional, that is not desired and not designed for by the manufacturer that designed the system. Overflow is purposeful right? It's what we as engineers design in as a fail-safe, right? So this, you can see an example of overflow in a wattle here. This is not unintentional bypass, undercutting a wattle, for example. This is purposeful overflow. And we did see substantial differences in performance for systems that had bypass versus IPDs that had overflow. And that's really why I'm drawing this distinction here. And then finally, dewatering time was simply defined as the amount of time from the end of the test to the point at which the system completely dewatered. So how much time in terms of minutes or hours did that take, all right? Okay, and without further ado, we will dive into our performance testing results here, but I did want to leave you before we go on to that with a quick video to show you the tests. You can see our trailer in the background here, active flow through this particular ditch section and into our inlet. You can see our sample tubing here that's taking our effluent samples. We also have a sensor measuring flows. So this just gives you a quick idea of the type of thing that we were doing to test out the performance of these IPDs. And again, we're measuring directly upstream and downstream of the devices is where we're taking our water quality samples. All right, let's dive into the results. I first want to bin the results and just compare the proprietary versus non-proprietary. As Justin mentioned, the non-proprietary devices are those that Ohio EPA currently has approved, and then proprietary are any number of different products that we tested that are on the market that a manufacturer constructs. As you can see here, the distribution of these two sets of data sets for our performance testing are relatively similar. And in fact, when you test these statistically, there's no difference between these two in terms of the effluent TSS concentrations coming out of the IPDs. So again, these are measured downstream of the IPDs, and this is representative of what would be discharged into the sewer system in this particular case. So no difference here between proprietary and non-proprietary for TSS. The same was true for turbidity, which I'm showing here. Again, non-proprietary on the left, proprietary on the right. And you can see the kind of distributions here switch, where there's more outliers for turbidity for non-proprietary and maybe some more outliers for TSS for proprietary. Again, no difference in either TSS or turbidity in terms of performance. The reason why we see more outliers in turbidity here, I believe, is that the non-proprietary devices had substantially more ponding in terms of peak ponding depth, and also in terms of dewatering time was much larger for non-proprietary systems, as we'll show you in just a bit as well. And so really we're dropping out large sands in the non-proprietary case, and we're not touching at all the silts and clays. And the silts and clays are what really contribute to turbidity for the most part in terms of reducing the clarity of the water, which is really what turbidity is a measurement of. So you can see some of those higher outliers here in that case, in this case, which we think is related to that, to those findings. Okay, I want to touch on what was perhaps the most important factor to water quality performance for IPDs, and that was bypass. I'll show you an example of bypass here in this video, wherein you can see this wattle being tested, and at the overlap, but at the ends of the wattles particularly, was a popular location for bypass to occur. This bypass would start almost immediately after the flow was started for the test and would continue throughout the duration of the test. So this bypass was, again, the biggest factor that we found that was really had a negative consequence on performance. You can see no bypass here in the salmon color, bypass in the sort of greenish blue color. And for both curb and ditch products, we had substantially higher effluent TSS concentrations, meaning dirtier water leaving when we had bypass. And that's because a fraction of the flow, and in some cases a substantial fraction of the flow, is really not being treated or controlled by the IPD. We also looked at IPD performance by the particular type, as Justin mentioned earlier. So above grade enclosures is the first box plot, and then as we go to the right, sheet covers, curb inserts, our non-proprietary devices are in the middle box plot here, undergrade baskets with curb guards, and then two different types of wattles in the two right-hand box plots. The gist of what we found for water quality performance by IPD type is that there was no difference. We were not able to tease out differences here in terms of effluent concentration of TSS as a function of the product type. So with regards to general product types, one over another, really what we would recommend is finding the one that fits the inlet that you're working with the best, because that will prevent bypass from occurring, which again was the most critical factor to our water quality performance for this particular project. I'll also mention briefly here dewatering time, just comparing non-proprietary on the left to proprietary systems on the right. You can see there was about a 35x difference in median dewatering time for non-proprietary versus proprietary products. Clearly, this for a curbed road particularly is a very important factor to consider if you have motorists that are traveling nearby to an inlet. This type of factor would be absolutely critical to understand, and clearly in this case, the proprietary systems have a tremendous advantage over the non-proprietary systems. Last thing I want to mention here is peak ponding depth. This is, again, as a function of IPD type. The IPD types are in the same order here as what I presented 2 slides ago. You can see the non-proprietary devices ponded water on average about 12 inches. The above grade enclosures were another one that tended to pond a lot of water, about 4 inches on average there. Again, those above grade enclosures are typically used in ditch cross sections, so maybe ponding there is not such a big deal. For the systems that are typically used on curb inlets, you can see the rest of those box plots there at maximum about 3 inches of ponding, and for some of them well less than 1 inch of ponding. So this gives you an idea of what we found across each IPD type for the peak ponding depth measured during the 30-minute hydrographs. All right, I want to talk next to longevity testing results, and then I'll pass it back to Justin to summarize. Longevity tests were done in 5 consecutive water quality hydrographs that were passed through the IPD without maintenance, as I mentioned, or replacement. So what we found generally was that the water level ponded higher and higher after each successive test as sediment accumulated in the product, around the product, etc. That would slow the flow rate down, thus creating higher peak ponding depths in subsequent tests. So in terms of water quality performance, we have effluent TSS here in the left-hand pane, and then we have dewatering time in the right-hand pane. And this is the successive test numbers. So the first test, followed by the second test, third, fourth, and fifth. Again, these are for IPDs that are not receiving any maintenance, not receiving replacement between each of the tests. And what you can see is a general trend where the first and second tests perform very similar to one another, really no decline in performance at all, essentially the same results. Then as we got to the third rainfall event that we simulated, we did start to see some sediment breakthrough here, and it continued into the fourth test, where we were getting subsequently increasing effluent TSS concentrations. The interesting thing we found, though, is that the fifth test actually saw a decline in median TSS effluent concentration. And we believe the reason for that is the general increase in dewatering time from test 1 to test 5 as sediment accumulated in the product. So we think what was happening is that we're essentially getting more ponding by the time we get to test 5. Therefore, we have longer retention time behind the product, and therefore slightly lower effluent concentration in this fifth test. Mentioned peak ponding depth here because that relates to the dewatering time on the previous slide. We generally saw increases in peak ponding depth, particularly from test 1 to test 2, and then kind of a flattening of peak ponding depth increases from there. Occurrences of overflow went to 1 out of 15 products in the first rainfall event, up to 2 in the second rainfall event, and then to 6 out of 15 products having overflow in the third, fourth, and fifth tests. So you can see effects here of that sediment accumulation on these IPD's performance. I think perhaps the most telling thing is to look at this visually, though, in terms of the extent of ponding that occurs behind an IPD as a function of the test number. Again, you can see the new product here in the left-hand picture, the end of test 1 in the middle, and the end of test 2 in the right. I think we'd all agree there's more and more sediment accumulating, not surprisingly. And what this causes is essentially the same flow rate to cause more and more and more ponding over time as you go from test 1 to test 2 to test 3, etc. This was true for above grade covers, as you see here. and it was true for most of the practices, if not all of the ones that we tested in this particular project. You can see an example here of an undergrade basket after test 2, after test 3, and after test 4. And the overflow was being used during test 4, and you can just see the amount, the mass of sediment here increasing test after test. So not surprisingly, the amount of ponding and the spread in that ponding increased as the test number increased. All right, so we're going to summarize here with our key findings of field testing, and then I'll pass it off to Justin. So sediment removal capability of proprietary devices was similar to non-proprietary devices. There was no statistically significant difference between those two. Untreated bypass related to poor product fit to the inlet was by far the most important factor here. And so finding a product that fits your inlet correctly in terms of its geometry is the most critical thing, we think, to obtaining good water quality function. Installation and initial water quality performance was worse for IPDs that required excavation. There were a few proprietary devices, and most of the non-proprietary devices required excavation. And as you can imagine, that resulted in loose sediment that was easy to wash off in the next subsequent rainfall event, in our case, simulated rainfall event. Peak ponding depths, dewatering times, and occurrences of overflow increased with successive longevity tests, and I think this really is not surprising. It speaks to the need to maintain these IPDs in the long run on construction sites and ensure their hydraulics are functioning well enough such that we're not impacting traffic or impacting other parts of the construction site. So really, this information that we learned on bullet 4 here was helpful in informing our maintenance guidance, which Justin's going to talk about in a second, which really indicated that after about a ½ inch of rainfall, which was essentially the end of our second test, we saw performance of these IPDs waning. And so we do think the current maintenance guidance of at least looking at these devices, if not performing some minor amount of maintenance after each ½ inch rainfall, actually is right on. So our study here was confirmatory of that ½ inch of rainfall threshold that is currently in the Rainwater and Land Development Manual. So with that, I will pass it off to Justin to take us home here.
All right. Thank you, Ryan, for that summary of all the data analysis and the performance data we collected from testing. Okay, so our next step after taking a look at all the data and all the results was to look at the products we tested, look at the results, and try to find turn that into recommendations to ODOT that they can incorporate into their future evaluation of products and incorporate into their qualified products list procedures in the future. So we looked for product material specifications, product characteristics, how they functioned, and just product properties that lended to better results and better installations, better treatment, ease of maintenance. So all these recommendations really kind of focus on getting a product that is going to operate, it's going to fit effectively, it's going to limit those unintended bypasses, it's going to be easily maintainable in the field, and it's going to have long-term success. So one of the key ones that we came on was all IPDs must have some sort of emergency overflow mechanism or some sort of secondary flow bypass feature, so that when they do get inevitably, clogged with sediment at some point, there needs to be an unobstructed flow path that the water can take so it can spill over and enter the inlet to prevent unnecessary flooding. So that can come in a multitude of different ways depending on the product configuration. Part of this research project, we also provided updated construction drawings, standard construction drawings for ODOT. So here's some examples you can see and how the different ways that emergency overflow can take shape and form. So for a wattle, that's just the area above the wattle itself. The water can flow over and enter the inlet untreated and acts as like a relief valve. Some of the above grate covers and the sheets that go over a grate, there needs to be some sort of opening, elevated opening that, again, the water can enter freely once the rest of the filtering material becomes clogged. For the above grate pop-up styles, again, the opening at the top, there has to be some kind of unobstructed opening for water to spill into. The undergrate baskets, many of them have an emergency overflow already cut into the side of them, which is good. And then depending on the inlet configuration, how these are installed, if there is a curb opening component to the inlet, obviously you need to block off the curb opening to prevent untreated bypass, but the overflow can be at the curb opening or in the basket itself. So there are options depending on the inlet and the product configuration, but as long as there's some type of emergency overflow path that the water can take, that's a big key. All right, the next kind of recommendation we came to is in regard to wattles, and again, preventing the untreated bypass, particularly at that overflow. So, we recommended a minimum overlap distance, and there should be sufficient staking to adequately secure the wattle to the ground to prevent undercutting and any flow bypass. And again, particularly at that overlap area, that's key. We also noted that lighter weight wattles and lower density wattles tended to be more susceptible to flow bypassing through undercutting or flowing under the device. So if a wattle is of lighter or lower density, it may require more frequent staking to securely fasten it to the ground surface. Next one, again, any trenching that's required to install these, we do recommend a minimum entrenchment depth to, again, prevent the bypass and the flow through underneath the material. So we recommended a minimum embedment depth of the filtering material as well as a minimum staking depth. And then it's really important to compact the backfill around the inlet protection device, around the excavation, recompact that loose soil down so that it's not going to be immediately resuspended and enter the inlet untreated. The next one is in regard to undergrate basket style products. In particular, it has to have some sort of physical attachment, or we recommend that it have some sort of physical attachment to the grate or to the inlet. This can come in the form of a strap or wrap around, something to wrap around the grate. It can also be in the form of a rigid frame that sits within the catch basin inlet itself, but it has to be suspended in a way or attached in a way so that when you lift the grate off, it doesn't just fall into the inlet. You'll see that sometimes with, like this example here, just a piece of geotextile under a grate, where if a maintenance person were to, try to clean this grate or this basket out, as soon as they lift that grate off, it's going to fall into the inlet. So trying to prevent that. So some sort of physical attachment, and that is, both for installation as well as for maintenance. It has to be maintainable without allowing sediment to spill into the inlet or the product itself to fall into the inlet. Along those same lines, limiting the untreated bypass. Like Ryan mentioned, that was sort of the most impactful factor in terms of effluent TSS water quality. So limiting those gaps, and in addition to like the wattle overlap, the other very common area where we saw untreated bypass occurring was when you had a product that had a curb opening attachment. Gaps between that curb opening attachment and the curb itself was a very likely, location where that can happen. So limiting those gaps, making sure it's a secure fit, and having a secure connection between that curb opening attachment and the curb itself is key to improving effluent water quality. The next one is that the IPDs should be installed within the gutter or within the curb line. We don't want any products that are installed in the travel lane itself. This is a very important factor for vehicle traffic, vehicle safety. So all of the devices have to be able to be put into a gutter, apron, or curb line and not in the travel lane itself. along those same lines, any product that secures underneath the grate or involves like lifting the grate to install it, we don't want to elevate the grate more than an 1/8 inch above the proper seated like grate elevation. Again, any sort of lifted frame that could cause an obstruction to a car, a cyclist, a pedestrian is going to be unsafe. So making sure the grate is not unnecessarily elevated as a result of the product installation is a key safety recommendation. So those are sort of the product properties and some of the inherent characteristics that we found would lead to successful inlet protection. Next, we looked at the material specifications for all the products we tested, and we tried to find correlations between the product performance and the material specs, and also compared those to ODOT's current geotextile fabric type C, which is what they use for silt fence, as well as for their geotextile inlet, the Ohio EPA geotextile inlet protection devices. And in general, the proprietary devices that we tested, those material specifications fell in line with ODOT's recommendations. A couple that I'll point out here, the elongation tear strength, we found that there could be some slight deviation, and those particular values could potentially be changed a little bit from ODOT's current recommendation. I think our biggest finding is probably permittivity. The current geotextile fabric has a very low permittivity, and that is most likely suitable for ditch inlet applications, 0.1 permittivity, because ponding depth is not such a critical factor, and you're going to get good treatment from ponding water. So because those are not installed on a ditch, or so those are installed in a ditch and not along a curb, not along an active travel lane, a lower permittivity and a longer dewatering time are probably permissible. But for applications where you're on a curbed roadway, an inlet that's right adjacent to a travel lane, we recommend a higher permittivity of at least 0.5. And that's in line with what we saw with the proprietary devices that we tested, which, as Ryan mentioned, had much lower ponding and dewatering time than the non-proprietary products. So we recommend a little higher permittivity if you're going to install a product on a curbed inlet. And then very similar related is flow rate. Flow rate is one of the key variables in permittivity. They're very correlated, and we saw correlation between those two. So again, based on the products we tested, the flow rate minimum should be in line with the permittivity, and based on the data we have, 38 gallons per minute per foot squared is the minimum flow rate through a geotextile device that we would recommend. Then the highlighted ones are just the ones where we differed a little bit from ODOT's current recommendations, current requirements. In terms of maintenance, as Ryan alluded to, our results were largely supportive of the current Ohio EPA frequency or maintenance frequencies as recommended in the Land Development Manual. So we have sort of three main thresholds we looked at. We have a duration threshold, which matches the current EPA guidance of inspect the devices every 7 calendar days or after a 0.5-inch rainfall event. It should be inspected within 24 hours following that rain event. Again, the sediment accumulation threshold in line with Ohio EPA, depending on the product type and the configuration, 1/2 of either the surface area, the height, the volume of the basket, basically half of the usable area, treatment area. Once that is compromised and caked with sediment, it should be maintained. And then we also recommended a dewatering time threshold. This we established about a 2-hour threshold. So this is based on the average dewatering time of the non-proprietary devices, which we see is on the very upper end threshold of dewatering for all the products we tested. So essentially, if a product's not dewatering within 2 hours after a rainfall event ends, it's probably clogged and it probably needs maintained. Again, this threshold being based on the non-proprietary devices are suitable for, definitely suitable for the ditch inlet configurations, but you could also potentially want to lower that threshold if you're in a curbed environment on a curbed roadway. So it really is kind of site dependent. If you want to have a lower threshold for dewatering time, you could. So that wraps up everything we've prepared today. I will go ahead and check to see the questions. I don't see any questions submitted at this time, but if there are any, oh, here we go. I see them coming through now. Let's see here. Okay. All right, bear with me here as I try to resize these windows. Okay, first question is, why do you think longer ponding times of non-proprietary practices why do you think the longer ponding times of non-proprietary practices resulted in higher turbidity? Does longer ponding time, settling time, make a spill or bypass more likely? Ryan, do you want to take that one for why the longer ponding times resulted in higher turbidity?
Yeah, I may have misspoke if that came across as the finding. I believe that the median, the middle value turbidities were almost exactly the same between the non-proprietary and proprietary devices. I believe, if I'm remembering correctly, one was 377 NTUs and the other one was 371 NTUs. So there was essentially no difference when you look across all of the data that we collected. There were some outliers to the high side on the non-proprietary devices. And that could be due to any number of things. Yeah, it could be bypass. But again, in terms of the overall findings, really no difference there in turbidity reductions. Yeah, I think as you saw with the particle size distribution that we put through these IPDs, it was heavily clay and silt focused. And so, with the relatively short retention times that we have with any IPD, right? We're not holding out of the water for periods of days or weeks. We're going to struggle to drop out those particulates via gravity.
And the second part of that question was, does longer ponding times make a bypass more likely? I don't know that we saw that. Yeah. Well, I don't know we saw that more likely. I think typically, if bypass is going to occur, it occurred usually immediately. Water tend to find the path of least resistance right away. And so if there was a gap somewhere, the water was going to go through there immediately. One potential, I guess the only example I can think of is for some of the products that require the embankment of the excavation and like the embedment. I think once the water ponded up a certain height, if it wanted to undercut and like pass underneath the material, like through the ground, that may occur if you had a higher ponding, just more head, more pressure, could force it through the ground and underneath the device when it's entrenched, which is why we recommended a minimum entrenchment depth for the material and the staking to prevent that.
Yeah, that's correct. Just to follow up on Justin's thought, some of the products were entrenched only 6 inches, and particularly when we got to relatively large peak ponding depths, we would see sort of undercutting of the water. So that is why that was one of the reasons why we had that major takeaway of at least 12 inches of embedment into the soil.
Okay. So yeah, thanks for that question. The next one, will the report be published showing results for each discrete product? The answer is yes. We will have a very lengthy appendix with product by product results and lots of good tables and graphs for everyone to review. Next one, for the wattle type IPD, did you consider different media types that would be more dense to hold the wattle in place? So yeah, I would say we tested a variety of different wattles with a variety of inner fill material at a variety of densities. So I think we do have, we looked at different density in heavier wattles and lighter ones. And that's where we kind of came to that conclusion that, the lighter wattles tended to require a little more physical restraint to hold them closer and more securely to the ground surface to prevent the undercutting. And then in terms of actually to hold, so other than like the product fill material, we followed the manufacturer guidance for any securing of the wattle to the ground. It was just manufacturer guidance. So we didn't necessarily change any variables ourselves. It was just whatever the product came filled with, that's what we tested, and we tested it and restrained it per installation instructions. And this one, depending on the products in play, will there be different frequency and inspection requirements for those that blind quicker? So right now, I think because our recommendations really fell in line, you know, like Ryan said, we saw the effluent water quality kind of make a quick decline after that second test, which corresponded really roughly with that 0.5-inch threshold by the EPA. So I think just in terms of a practical standpoint, we've only recommended that they all be inspected at the same frequency. Is the long story short. Just again, from a construction practicality, doing it all on the same routine frequency is going to be the most sustainable and just ensure the best, that they're all being inspected properly, I guess.
Just to add to that, Justin, I think the frequency of maintenance, though, will change with blinding, right, as a function of that, you know, requirement to maintain after the device is half full of sediment, right? So the frequency of checking is the same, right? Going to actually visit the IPDs after rainfall events, but the maintenance frequency will differ as a function of how fast they blind. Yes.
That's a very good point. Yes. So yeah, the frequency will remain the same, but yeah, depending on how much sediment accumulates, they may need to be maintained more or less frequently. Do wattles stay within the footprint, or are they not allowed due to the extension into traffic? So I think it really comes down to like an installation, like site-by-site kind of location. I think for a wattle to be used, like adjacent to a roadway, it would have to be the right characteristics where it could be installed out of traffic. And a lot of that, there's limitations, I know, to like the installation of a wattle in that scenario. There are some wattles that are designed because they're heavy and dense enough to remain in place without additional restraint. And when appropriate, those could be used as long as they were secure, you know, as long as they're heavy enough to be secured to the ground through the self-weight. But again, if you're installing it next to a roadway, it's hard to stake them, obviously, because you're in impervious area. Next one, when will the published results be available and where will we find the study? So results, we are delivering our final results to ODOT on March 13th, and ODOT will review that and make them available on the research website as soon as they can. I don't know the specific date, but should be available shortly. How were the proprietary inlet protection products that were tested selected? Was it based on how frequently they are used in the field? So we, again, compiled like a comprehensive list of all the products we found available, and then the report will outline the very lengthy procedure we used. We looked at ones that were readily available in Ohio, ones that ODOT had experience with. We looked at the product materials, the characteristics, so that we could have a good cross-section of products, so we could compare things like fill material and geotextile material type. We wanted to make sure we were kind of testing a variety of products and a variety of characteristics so that we could draw conclusions and try to figure out what pros and cons each of those had. And then the use or the selection of the products we're testing in our research will have no bearing on whether or not that product's allowed or not on an ODOT project. We just use it to inform and come up with some characteristics and recommendations to ODOT that they can use in their evaluation process.
I would just add to that, Justin, the other real mechanism by which we chose IPDs was to ensure that we had a good cross-section of IPDs that would fit the various different types of inlets that are typically used in the ODOT environment. So that was another key factor, was trying to make sure that we had a good cross-section of IPD types that fit each respective inlet that you saw.
Yeah, very good point, Ryan. Thank you. That's all the that's all the questions, I'm sorry, that I see submitted now. If there's anything else, I'm sure you can follow up, and we're happy to answer any questions and discuss further at a later date. But yeah, with that, I'll conclude our presentation.
Thank you all so much for your time. And again, I'll send out a follow-up email. Have a great day.